Hello and Assalamualaikum to both my examiner. My name is Rosma Muhazim bin Marzuki, and today I will be presenting my final year project which focus on synthesis and characterization of manganese 2 and zinc 2 metal complexes. So, this first chapter introduces Schiff base, which are ligands formed from the condensation of primary amines with aldehydes or ketones, resulting in imine or isomethyl groups. This Schiff base can bind with transition metals, forming metals complexes through coordination bonds. The chapter highlights the versatility of Schiff base, particularly those derived from aliphatic diamines and salicyl aldehyde, which produce silane-type ligands. These ligands are significant in coordination chemistry due to the adaptability and range of application, including catalytic, enzymatic, magnetic, and pharmacological uses. The chapter underscores the importance of understanding the structure and properties of Schiff-based metal complex, specifically those involving manganese 2 and zinc 2, to explore the potential applications. Chapter 2 provides a comprehensive literature review on Schiff bases, organic compound formed by the condensation of primary amines with aldehydes or ketones, thus resulting in C-double bond N imine group. Named after chemist Hugo Schiff, these bases play a crucial role in coordination chemistry, serving as ligands in metal complexes with application in material science, bioinorganic chemistry, and catalysis. Schiff base exhibit diverse biological activities including antibacterial, antifungal, anti-cancer, and antiviral properties, making them valuable in chemical sciences for environmental monitoring. They are also versatile in applications such as catalysts, particularly when complex with transition metals, and in color chemistry as intermediates in chemical synthesis. The synthesis of Schiff base typically involve the condensation of primary amines with aldehydes or ketones. This research focused on Schiff base derived from aldehydes and aliphatic diamines, specifically using salicyl aldehyde and 2,2-dimethyl-1,3-propane-diamine or DMPD. Previous studies have shown that Schiff base metal complex with palladium, platinum, zinc 2, and nickel 2 exhibit positive antibacterial activity with selectivity depending on the type of Schiff base and metal complexes used. For research methodology, firstly, the synthesis of Schiff base are following these steps. The synthesis of Schiff base was using the ratio of 1:2 diamine-to-aldehyde. In this research, 5 mmol of the MPD was dissolved in 15 mmol of ethanol, then 10 mmol of salicyl aldehyde was also dissolved in 15 ml of ethanol. The ethanolic solution containing 5 mmol of the MPD was slowly added into ethanolic solution containing salicyl aldehyde with continuous stirring. The solution was then refluxed for 4 hours. All the steps was repeated again by replacing salicyl aldehyde with 5-chlorosalicyl aldehyde and 5-nitrosalicyl aldehyde, which means 3 Schiff base will be produced. Next, the synthesis of metal complexes. 1 millimole of the synthesized Schiff base was dissolved in 10 ml of ethanol, and 1 millimole of metal was also dissolved in ethanol. This ethanolic solution containing the dissolved metal was then slowly added into ethanolic solution containing Schiff base with continuous stirring. This step done for 6 times by changing the pair of Schiff base and metal respectively. For this thesis, 6 metal complexes was obtained. For the last part, which is the characterization of Schiff base and its metal complexes, 5 characterization technique was used. The first one is elemental analysis, followed by melting point analysis. Next, IR spectroscopy was done using KBR pellet, and UV-vis spectroscopy was also done using dilution factor of 10 power of negative 4 and 10 power of negative 5. Lastly, molar conductivity analysis was done by diluting the metal complexes in acetonitrile. Next part is for results. First is ligand L1 made from the MPD and nitrosalicyl aldehyde. It has a molecular weight of 429. Using ethanol as dissolvent, it was refluxed in a 2:1 ratio for 4 hours, resulting in a yellow precipitate with a 67% yield and a melting point of 199.5 to 207.3 degrees Celsius. For the manganese L1 complex, using a 1:1 ratio with a 6-hour reflux, a yellow precipitate with an 81% yield and a melting point over 400 degrees Celsius was obtained. The zinc L1 complex made under the same condition gave a light yellow precipitate with a 77% yield and a melting point above 400 degrees Celsius. Next is ligand L2 from the MPD and chlorosalicyl aldehyde with a molecular weight of 379.28. Refluxing in a 2:1 ratio for 4 hours with ethanol, a yellow precipitate was obtained with a 52% yield and a melting point of 130.2 to 136.7 degrees Celsius. For the manganese L2 complex, a 1-to-1 ratio with a 6-hour reflux gave a black precipitate with a 32% yield and a melting point over 400 degrees Celsius. The zinc L2 complex under the same conditions result in a light yellow precipitate with a 47% yield and a melting point above 400 degrees. Finally, ligand L3 made from the MPD and salicylaldehyde with a molecular weight of 316.12. Using ethanol and a 2-to-1 ratio with a 4-hour reflux, a yellow precipitate was obtained with a 45% yield and a melting point of 98.7 to 122 degrees Celsius. For the manganese L3 complex using a 1-to-1 ratio with a 6-hour reflux, no yield was recorded. The zinc L3 complex made under the same condition resulted in a white precipitate with a 67% yield and a melting point above 400 degrees Celsius. The IR spectroscopy data for ligands L1, L2, L3 and their metal complexes with manganese 2 and zinc 2 reveal how metal coordination affects vibrational frequencies. For L1, the C double bond end stretching frequency shift from wave number 1649 to 1615 in manganese L1 and 1333 in zinc L1, indicating interaction with the metals. CN stretching in L1 shift from wave number 1318 to 1304 in manganese L1 and wave number 1330 in zinc L1, while a new CO stretch appears at around wave number 1106 in the metal complexes. The MO stretching frequencies at 510 for manganese L1 and 518 for zinc L1 confirm metal coordination. For L2, the C double bond end shift from 1631 in L2 to 1591 in manganese L2 and 1626 in zinc L2. The appearance of MO stretching at 475 for manganese L2 and 465 for zinc L2 further confirms coordination. Similar shifts are observed for L3 with the C double bond end stretch moving from wave number 1722 in L3 to 1722 in zinc L3 and the CO stretch at around 1075 in the metal complexes. MO stretching at wave number 473 for zinc L3 confirms the interaction. This shift and new peak indicates that the metal ion, manganese and zinc coordinate with the ligands, altering the vibrational frequencies of the involved functional groups and help in understanding the structural changes and bonding nature in the metal complexes compared to the free ligands. UV spectroscopy measures the light absorption of a substance at different wavelengths, revealing its electronic structure. The spectrum for ligand L1 shows peak around 190 to 400 nanometer, representing electronic transition pi to pi star, where electron moving from bonding to antibonding orbitals, and n to pi star, where non-bonding electrons moving to antibonding orbitals. The structure of ligand L1 highlight how its chemical group influence its electronic properties. The manganese L1 spectrum shows similar peaks but slightly shifted due to the manganese ion altering the ligand's electronic environment. This change affects how the ligand's electron behave, resulting in different absorption characteristics. The zinc L1 spectrum also displays pi to pi star and n to pi star transition with peaks slightly different from both the ligand and the manganese complex. The zinc ion's interaction with the ligand leads to unique absorption properties. The spectrum for ligand 2 exhibit prominent pi to pi star transition at shorter wavelength around 210 to 230 nanometer and 270 to 280 nanometer, alongside a smaller n to pi star transition around 310 nanometer. The spectra for the metal complexes manganese L2 and zinc L2 show similar peaks, indicating that these transitions are preserved upon coordination with the metal ions. However, there are slight variation in the intensity and exact position of the peaks due to the influence of the metal centers. Ligand L3 spectrum with peaks from electronic transition pi to pi star and n to pi star influenced by its aromatic rings and hydroxyl group. The zinc L3 spectrum where the peak shift due to the changes in the electronic structure when zinc bind to the ligand. This illustrates how ligand L3's UV-based absorption properties alter upon forming complex with zinc. In conclusion, the synthesis of SCHIFF base was successful since it matched the theoretical data, while the synthesis of metal complexes was unsuccessful after characterization of these compounds was performed. Although the CHN value of manganese L2 shows almost identical value with the theoretical data, but the presence of off-match peaks in the IR shows that either the synthesized compound was not homogeneous or contained interference. For recommendation, X-ray crystallography should be included in the characterization method to provide insight on the structure and geometry of the compounds, especially metal complexes.